Section 4.5 exercises. Problem 1. We're asked to find the exponential growth model given the information stated above. And what we'll do here is we will let t be the number of years since the year 2000. By aligning the data in this way, that means that t equals 0 will correspond to the year 2000, and then t equals 11 will correspond to the year 2011. So that translates to given two ordered pairs. T is 0, the population is 807 million, and when t is 11, the year 2011, the population is 1,052 million. A, 0, corresponds to when time is equal to 0, and that is the population at that time, 0. So A0 is 807. So we can write our exponential growth model to be A equals A0, 807, e to the kt. Now we use the other ordered pair, 11, 1052, to find the growth value k. So 1052 is the population, equals 807. E to the k we have to find, and t is 11 years later. So we'll find k by using logarithms. First divide by 807. 1052 divided by 807 is equal to e to the 11k. Now we'll take natural logs of both sides. Natural log of 1052 divided by 807 is equal to the natural log of e to the 11k. So the natural log of 1052 divided by 807 is equal to 11k natural log e. Natural log e is 1. So we'll have 11k is equal to the given logarithm, and dividing both sides by 11 will give us the natural log of 1052 divided by 807. All divided by 11 will be our value of k. And on the calculator, we need to get a decimal approximation for that, and we'll write 0.024 as its value. That means we now have the growth model. A equals A0, 807, e to the k, 0.024 t. So now given a value of t, we can find the population A, or given A, we can use logarithms to find the value of t. In the next part of problem 1, we are asked to find t so that A is 2,000, since we're given the population to be 2,000. So 2,000 is equal to 807 e to the 0.024 t, and we'll find t using natural logs just as we did up above. First, isolate the exponential and divide through. Now take the natural log of both sides, and the natural log of the right side. Now use the power property of the logarithms by putting the power down in front of the logarithm. So the log of 2,000 divided by 807 is equal to 0.024 t log e, which is a 1. So now just divide both sides by 0.024. So the natural log of 2,000 divided by 807, all divided by 0.024 is our value for t. Getting a decimal approximation for that on the calculator, we find that t is approximately 38 years. It'll take approximately 38 years for the population to reach 2,000 million or 2 billion. Let's go to problem number 2. This is a logistic model, and we're asked to find the proportion of correct responses after 10 learning trials, where t is the number of learning trials. So here we are given t being 10 and asked to find the y value, which is the functional value after 10 learning trials. So this is direct substitution into the function. F of 10 will be 0.8 divided by 1 plus e to the negative 0.2 times 10, which is approximately 0.7 after working that through on the calculator. So after 10 learning trials, the proportion of correct responses is approximately 0.7. The next part, we're asked, what is the limiting size of f of t? As the number of learning trials take place, more and more learning trials take place. So to translate, we're asked to find f of t given that the number of learning trials t increases without bound. What I suggest doing is first rewriting our function f of t. The given function is 0.8 divided by 1 plus e to the negative 0.2t. I'm going to rewrite that as the exponential in the bottom I'm after. E to the negative 0.2t is e to the positive 0.2t. And the reason why I did that, as t grows, as the number of trials become larger and larger and larger, this fraction right here, 1 over e to the 0.2t, approaches 0. So f of t, the number of learning trials, as t grows without bound, will be approximately 0.8 divided by 1 plus 0, or 0.8. Let's go on to problem number 3. Here we have a table of population versus the walking speed of people who live in that population. And we are asked to draw a scatter plot of the data and determine what function might be best. So here I have chosen to draw this by hand. So we have the population here, and we have the walking speed here. So we'll tick off the axis here in a meaningful way, maybe by 0.5s. And we'll tick off the horizontal axis, say by 50s, 100, 200, 300, and 350 there. And we'll plot these points. Population of 5.5 thousand gives us a walking speed of 0.6, so that's approximately here. And population of 14,000 gives us 1, it's approximately here. And population of 71,000 gives us about 1.6, so about here. And 138,000 gives us a walking speed of about 1.9. And finally, 342,000 population gives us a walking speed of about 2.2. So about here. Function that has a very sharp initial rise and a very slowly increasing graph as a lot of the variable increases. This is a classic shape of a logarithmic function. And this is probably the best model to use for the scatter plot. Problem number 4. We have to rewrite an exponential function that's in the form p equal p0 times a to the t, and we want to write that in a continuous exponential, p equal p0 e to the kt form. So our exponential, 4 times 7.8 to the t, has to be equal to the same initial value with exponential growth e to the k times t. What I'll do on the right-hand side, after dividing through by 4, is I will rewrite the right-hand side using rule of exponents, e to the k, all to the t. And the reason why I did that is you have now t as exponent on both sides, which means the bases must be the same. So 7.8 must be equal to e to the k. So now we take logs of both sides to find the value of k. Log of 7.8 is equal to log of e to the k, or on the right-hand side, k times log e is equal to the log of 7.8. And log of e is 1. So k is the log of 7.8, and that is approximately 2.054. So the exponential function y equals 4e to the 2.054t is exactly the same as the given exponential function y equals 4 times 7.8 to the x. This is continuous growth, and this is called discrete growth.